Okay, in this video we're going to talk some more about circuits, and I'd like to start by revisiting the battery. And this particular battery is 1.5 volts. And when we draw pictures of circuits, those are called schematics. We have symbols for all the different kinds of components that can be in the circuit. And the schematic symbol for a battery looks like this. It's a long line and a short line. And maybe I'll put a couple of wires coming off of that. And that symbol represents this. Now the long line is the plus end of the battery, and the short line is the minus end of the battery. And you can see that on these batteries there's a little plus symbol right here that's on the sort of the nipple end of the battery. That's the long line end of the battery in the schematic symbol. Now you might think, well, can I put more than one battery in a circuit? And the answer is yes. In fact, there's a couple of common ways that you can put multiple batteries in a circuit. One way is to stack them, sort of like this, one on top of the other. That's the way that you put batteries into a flashlight. Now, assuming that each one of these batteries is 1.5 volts, what do you think would be the voltage of 3 batteries hooked together like this? Well, if you guessed 3 times 1.5 volts, or 4.5 volts total, you would be correct. So let's go ahead and check that. I'm going to take my voltmeter and I'm going to put one end of it on one side of this stack and one end on the other. And you can see it reads 4.6 volts, which is pretty close to 3 times 1.5 volts. So when we have batteries stacked together this way, we say the batteries are in series and their individual voltages are going to add. So if I wanted to draw that in a schematic, I would draw it something like this. Okay, where I'd have 3 of them all stacked together. Remember, in each symbol, the long line is the plus side, and the short line is the minus side. So if I have my wires coming off like this, and I measure the voltage between these 2 points, it's going to be equal to the sum of all these individual battery voltages. So we say this is a series arrangement of batteries. Another way that you can put batteries together is in what's called a parallel arrangement. And let me draw you what a parallel arrangement looks like. So we have batteries, but instead of stacked one on top of the other, we have them sort of side by side. And we have all the plus sides connected together, like this. Each of these is the plus side where the long line is. And we have all the minus sides hooked together, connected together, something like this. And so this is the overall plus side of the battery pack, and this is the overall minus side of the battery pack. And when you hook them together, this is called a parallel arrangement. And when you hook the batteries together this way, you don't add voltages. The voltage is basically just going to be the same as any individual battery. And I can show that by using a couple of metal strips here. Here's a metal strip, and I'm just going to stack 3 batteries and put them on that metal strip like so. And then I'm careful to make sure that all the minus sides are touching the battery strip, or the metal strip. And then I'll make sure that all the plus sides, the nipple sides, are touching another strip, like this. And then what I'm going to do is I'm just going to measure the voltage between the 2 metal strips. And it might be easier said than done here. So when I measure that voltage, what I get is 1.5 volts. That's just the voltage of one of the batteries. So I don't get any kind of voltage advantage by putting batteries in parallel. But what I do get is the battery's pack will last 3 times as long as an individual battery. So that's why you want to put them in parallel. Not to get more voltage, but to get more longevity out of your battery pack. Now, in a previous video I showed you a resistor, and in another video the concept of resistance was sort of defined. Resistance has symbol R, and R is for resistance. And resistance is measured in the units of ohms. and ohms has a symbol, Greek letter omega. So all resistors have different amounts of resistance. This particular resistor, if you look at it very closely, it says 30 omega, or 30 ohms. That's how much resistance it has. I want to go ahead and measure that to confirm that that resistance that's printed on the resistor is pretty close to what its actual resistance is. Its actual resistance is 30.1 ohms. 30.0, that's pretty good. 30.0 ohms. So I have the multimeter now configured to measure resistance. So that one looks okay. This one is, if you look at it, it says 10 ohms. So we'll go ahead and measure that one. And according to my multimeter, this is really closer to about maybe 10.3 ohms. So we had a 30 ohm, and we have 10.3 ohms. And then the last resistor I have, it's written on the side, it says 20 ohms. But I'm going to go ahead and measure that with my meter. And this is close to about maybe 20.2 ohms. That's not too bad. Now the schematic symbol for a resistor looks like this, kind of a zigzag line. And then you write the value of the resistor by the resistance, or by the symbol. And so I want to figure out what the resistance would be if I took these three resistors and I hooked them up in series. Okay? So one of these resistors is going to be 30 ohms, and the other is going to be 20.2 ohms, and the other one's going to be about 10.3 ohms. I'll put a little terminal symbol there. And if I took my ohm meter and measured the resistance across all three, what do you think that ohm meter would read? Well, from the video, you should have learned that when I have resistors hooked up in series, that the equivalent resistance across all the resistors that you have hooked up in series is just equal to the sum of all of the individual resistors. So in this case, RE, which stands for R, equivalent resistance, would be equal to 30 ohms plus 20.2 ohms plus 10.3 ohms. And if I add those together, that's going to be 60.5 ohms, I think. 60.5 ohms. That's 60.5 ohms. So what I'd like to do here is actually do that. I'm going to hook all these resistors together with these little alligator clips, and we'll measure the resistance across the whole, all three of them hooked together. So here I've clipped two of them together, and now I'm going to clip these two guys together with my alligator clip. So everybody's all clipped together, and I'm going to take my my meter here, my multimeter. I'm going to hold one probe on one end and one probe on the other end, and we'll see what the multimeter says. Okay? So here we go. One probe, holding it nice and tight, and we get about 59.7 ohms. So 59.6 ohms. So a little bit less than what we predicted, but that could just be problems with the accuracy of the meter. So at least we're in the ballpark. We're measuring about 60 ohms, and we predicted about 60 ohms for these three resistors in series. Now, there's another way that you can put resistors together. You can put them together in parallel, and that looks something like this. Here would be one resistor, here would be another resistor, and here would be another resistor. And all the ends of one side of the resistors are hooked together, and all the ends of the other sides of the resistors are hooked together. And you would be measuring the resistance, the equivalent resistance of all of them by measuring between those 2 points. And you could put as many of these in this arrangement as you want. So using our three resistors as an example, remember one of them was measured to be 30 ohms, and one of them was measured to be 20.2 ohms, and the other one was measured to be 10.3 ohms. If I want to measure the equivalent resistance of all of these guys together, I have to use another law. I can't just add them together like I did for resistors in series. So this is parallel resistors. Okay. What I need to do is I need to use the following rule. The reciprocal of the equivalent resistance is equal to the sum of the reciprocals of each resistor. Okay? Now you can't just add them all together and take the reciprocal. You have to take the reciprocal of one plus the reciprocal of the other plus the reciprocal of the other, press equals on your calculator, and then you have to take the reciprocal of the whole thing. So let's see what that would be in the case of our resistors, at least theoretically. And I want you to watch very carefully how I'm doing this, okay? First of all, I'm going to take the first resistor, which is 30 ohms, and I'm going to put in 30. And then I'm going to hit the reciprocal key, which is that key there. Then to that, I'm going to go plus 20.2. That's the second resistance. And then I'm going to hit the reciprocal key again. And then I'm going to plus 10.3 and hit the reciprocal key again. And then I'm going to hit enter, which is adding all the reciprocals together. But now I need to take the reciprocal of my answer. And to do that, I'm going to go second function, and then come down here to answer. That retrieves this answer that I just did. And then I'm going to hit reciprocal one more time. And then I'm going to hit enter. And my total resistance, equivalent resistance, should be about 5.6 ohms. So let's go ahead and check that to see if that in fact is the case. So what I'm going to do here is I'm going to take my three resistors and I'm just going to kind of lay them down here. And I'm going to take one strip of metal, I'm going to put them over one side, and one strip of metal and put her over the other side, and I'm going to press down really hard with my little leads here on the two metal strips, and let's see what the meter says here. So if I do this and I press down really hard, I'm getting about 5.7 ohms, which is pretty close to the 5.6 ohms that I predicted. So that's how you do resistors in parallel. Now, I can draw these resistors in parallel in different ways. For instance, I could have a circuit that looks like this, and maybe like that, and maybe like that. And those resistors are also in parallel. In fact, this circuit arrangement is identical to this circuit arrangement. It's just drawn in a different way. Okay? So don't be confused about the way the components are drawn. These are three resistors in parallel next to one another, and the ends of all the resistors are hooked together on one side, and the ends of all the resistors are hooked together by a wire on the other side, and you're just measuring the resistance between the two wires. Well, that's the same situation here. On one side, all the wires are hooked together. On the other side, all the wires are hooked together, and you're measuring the resistance between the two sets of wires. Now, one of the videos talked about Ohm's law. And Ohm's law says that V is equal to I times R, where V is the voltage between any two parts of the circuit, I is the current that's running between those two parts, and R is the resistance or equivalent resistance between those two parts of the circuit. So let's make a simple circuit and verify Ohm's law. So I'm going to take a battery. Remember, that's a long line and a short line. And that's going to be 1.5 volt battery, and you'll have a plus side and a minus side, and we'll hook it up to a 30 ohm resistor, just like this. And what we want to do here is we want to measure, first of all, confirm that the voltage across my resistor is in fact 1.5 volts. And we're going to do that with a multimeter configured as a voltmeter. And sometimes if I want to add the voltmeter to the circuit, I put another little part of the circuit on there with a V in there. V stands for voltmeter. So these are the two probes of the voltmeter that are hooked up on either side of the resistor like that. Okay? The other thing I want to do is I'm going to want to measure the current going through the circuit. Now this is going to be a series circuit, so the electric current should be the same everywhere. And in order to measure electric current inside a circuit, you have to actually physically break the circuit and put the current meter or ammeter inside the circuit and make it part of the circuit. So when I draw that as a part of my schematic diagram, A stands for ammeter or current meter, measures current, and we're actually making it part of the circuit. So I'm going to be measuring the voltage across the resistor, the current through the circuit, and hopefully that current times that resistance will equal my voltage, or at least is close within the accuracy of the measuring equipment. Okay? So let's go ahead and do that really quick. I have the circuit set up here. I'm using a little battery holder here to hold the battery. That's going to make things a little bit easier. And I want to make sure that the red wire is hooked up to the positive side of the battery and the black wire is hooked up to the negative side of the battery. That just makes things easier to remember. There's no difference between the wires other than their color. So now both sides, these wires are now going through the resistor here. So the first thing I want to do is I want to measure the voltage. So I'm going to have this thing hooked up like a voltmeter. Move this off to the side here. Kind of moving my battery off camera. So right now this is hooked up as a voltmeter. So I want to put one probe on one side of the resistor and one probe on the other side of the resistor. Get my arm out of the way. It reads about pretty close to 1.5 volts, as we would expect, having this hooked up to a 1.5 volt battery. So I'm going to write this down, 1.5 volts. Now I'm going to measure the current. I'm going to measure the current by breaking the circuit here. And then I'm going to configure this multimeter as an ammeter to measure electric current in amps, actually in milliamps. And I'm going to put my little current meter here. And I'm going to put one probe of my current meter in the alligator clip that used to be hooked up to the resistor here. And then the other end of the current meter I'm just going to hold on to the end of the resistor. So now I'm measuring the current going through that part of the circuit. It's about roughly 43 milliamps. So let's write that down. I is equal to 43 milliamps, which is the same thing as 0.043 amps. Because remember, 1,000 milliamps is equal to 1 amp. So let's see what I times R is. I times R is going to be 0.043 amps times the voltage of 1.5, times the resistance, which in this case is 30 ohms, sorry. And I multiply those two together, and I get 0.043 times 30, and I get about 1.3 volts. Okay, that's a little bit less than the 1.5 volts I measured. It's possible that we have some issues with the accuracy of my meter. Okay, now I'd like to analyze a little more complicated circuit here. Let's suppose we have something that looks like this. We have our 1.5 volt battery, and it's now going to go through 3 resistors instead of just one resistor, or hooked up to 3 resistors. And furthermore, I want to put an ammeter in this circuit so I can figure out what the current is. And I want to put a voltmeter across each resistor. Actually, it's only going to be 1 voltmeter, then I'm going to take 3 measurements. But it's the equivalent of doing something like this, where these 3 V's represent the voltage across the first resistor, across the second resistor, and across the last resistor, and then my current meter here to measure the current going through the entire circuit. Let's make this 10 ohms, 20 ohms, and 30 ohms. My resistors are maybe not exactly these values, but they're going to be close enough. And what I like to do is predict what each one of these values is going to be. And I'm going to do that using Ohm's law. V is equal to I times R. And I'm going to use Ohm's law in different ways. The first thing I want to do is figure out the equivalent resistance of all three resistors together. So R equivalent is going to be equal to 10 ohms plus 20 ohms plus 30 ohms. And I'll add that all together because they're in series, and I'm going to get 60 ohms. The next thing I'm going to do is use that equivalent resistance and Ohm's law to figure out the current going through the entire circuit. So I'm going to imagine replacing these three resistors with one resistor of resistance 60 ohms. That's really what I mean by an equivalent resistance. I'm taking these three resistors out of the circuit and replacing them with one single 60 ohm resistor. And so if I do that, I'm going to figure out the current the way I figured it out before, using Ohm's law. V is equal to I times R, which implies that I is equal to V divided by R. So the voltage across that equivalent resistance will be the voltage of the battery, 1.5 volts, divided by that equivalent resistance, I guess I should put E for equivalent in there, of 60 ohms. And when I do that on my calculator here, 1.5 divided by 60, I should get 0.025 amps. And that's the same thing as 25 milliamps, because that's what my meter is going to read. So that's one of the things I'm going to check, how close we're getting to 25 milliamps, keeping in mind that my meter appears to be a little bit off. Now what I want to do is use this and Ohm's law to figure out the voltage across each resistor. So to do that, I just take the resistance of the particular resistor in question, that's R, multiplied by the current going through the resistor, which is for all three resistors is going to be the same 0.025 amp current, and that will give me the voltage across that individual resistor. So let's do that in each case. So I'm going to say V10. Subscript 10 means I'm trying to find the voltage across the 10 ohm resistor, is going to be equal to that current, 0.025 amps, going through that resistor, times the actual value of the resistance, which is 10 ohms. V20 is going to be equal to 0.025 amps times 20 ohms, and V30 is going to be equal to 0.025 amps times 30 ohms. And I'll figure this out real quick in each case. Well, this is easy. That's just going to be equal to 0.25 volts. This will be twice that amount, which is 0.50 volts. And this will be 3 times that amount, which is going to be 0.75 volts. Now notice if I add all these together, what I get is 1.5 volts. That's equal to the boost in the battery. So what's happening here is that for every coulomb of charge that passes through the battery, it's going to get 1.5 joules worth of potential energy. It's going to lose 0.25 joules going across the first resistor, 0.5 joules going across the next resistor, and finally 0.75 joules going across the last resistor, and it's going to end up back at 0 joules, and the cycle will complete. So this is a voltage boost. Each of these three things are voltage drops. The sum of the drops has to equal the boost. Now let's go ahead and measure these quantities with an actual circuit. So here I have a 10 ohm, a 20 ohm, and a 30 ohm resistor all kind of clipped together in series. Let's measure the voltage across the very first resistor, which is this one here. And, oops, I got the leads flipped around here. Let's do it this way. And as you can see, it's pretty close to 0.25 volts, which is exactly what we predicted it to be. Let's look at it across the second resistor. which looks like that. And that's pretty close to 0.5 volts, which is what we predicted it would be. And then across the last resistor, that's, well, it's 0.76 volts, but again, pretty close to what we predicted it to be, of 0.75 volts. Now let's go ahead and configure our meter to measure current. And I'm going to break the circuit like I always have to do in order to measure the current. And I'm going to put my one lead, I'm just going to clip onto the alligator clip going to the battery. And then the other lead, I'm going to just kind of hold it up there. And it looks like it's pretty close to 24 milliamps. And we predicted that it would be 25 milliamps. So the physics is looking pretty good here. So now I'd like to analyze a different kind of circuit. This is going to be a circuit where I have 3 resistors in parallel. So I'm going to start off with my standard 1.5 volt battery here. And that's the plus side. And then I'm going to have the current coming off of that battery go through 3 resistors, like this. And I'm going to want to measure the current going through each one of these resistors. So I'm going to put an ammeter to measure current. I'm not really going to use 3 different ammeters. I'm just going to use one single ammeter 3 times. But you can represent it schematically with these little circles with A's in them. And then I'm going to measure the current going back into the battery as well. Furthermore, I'm going to measure the voltage across the whole thing with a voltmeter. And that's going to look like this. One thing I haven't really mentioned about voltmeters and ammeters. For an ammeter to work properly, the resistance of the ammeter itself must be 0. In other words, it must behave like a wire. The circuit can't know the difference between having an ammeter in it and just having a wire going through that point. Similarly, a voltmeter has to have effectively infinite resistance. It can draw no current. The circuit has to think like it's not even there, okay, for it to give an accurate measurement. So let's suppose these 3 resistors in parallel are 30 ohms, 40 ohms, and 50 ohms. And we'd like to figure out what those currents are going to be. Well, first of all, the voltage across this circuit is just going to be 1.5 volts. If I were to take my voltmeter here and put my 2 probes like this, I would obviously measure 1.5 volts. I'm just measuring the voltage across the battery. But I could take this probe and move it along, and it would still read 1.5 volts anywhere along this circuit. Okay? Anywhere along here, as long as I don't jump across a resistor or jump across a battery. 1.5, 1.5, 1.5, 1.5, 1.5. Or I could hold the red probe here and then move this guy anywhere along the circuit here, and I would still read 1.5, 1.5, 1.5, 1.5. Because all these things are is just pieces of conducting wire. So there's going to be no voltage change as I move along the wire. There's only going to be a change in voltage if I jump across a resistor or jump across a battery somehow. Okay? So this voltmeter doesn't matter how I hook it up as long as one side of it is on one side of the circuit and the other side of it's on the other side of the circuit. Similarly, I can take the ammeter and put it up here on the other side of the resistor, and it's going to read the same thing because the current going through the single branch there is going to be the same everywhere within that branch. So the way we actually figure this out using Ohm's law, V is equal to I times R, is we solve this for current. I is equal to V over R. And the V is going to be the same everywhere in this circuit. It's going to be 1.5 volts. So the current going through the 30 ohm resistor is just going to be equal to the voltage across that resistor, which is 1.5 volts, divided by the value of the resistor itself, which in this case is 30 ohms. Similarly, for the 40 ohm resistor, the current going through it is 1.5 divided by 40 ohms, and through the 50 ohm resistor, 1.5 volts divided by 50 ohms. And we work this out and we get 0.05 amps, which is equal to 50 milliamps. And this one's going to be equal to 0.0375 amps, which is equal to 37.5 milliamps. And then finally, this is going to be 0.03 amps, which is the same thing as 30 milliamps. Furthermore, the currents are going to kind of come back together and add up all together going back into the battery. So this sort of total current, I'll call it I total, put a little T here for total, that's just going to be equal to I30 plus I40 plus I50. And when I add all those guys together, I'm going to get 50 plus 30 plus 37.5. That's going to give me about 118 milliamps roughly of total current. And that's what we should be measuring here as all the currents come back together again. Now I've actually set up the circuit that we were just analyzing. I have the three different resistors in parallel, the 30 ohm, the 40 ohm, and the 50 ohm, sort of taped down on my desk. And the tops of all these resistors are hooked together by this top metal strip, and the bottom ends of the resistors are hooked together by this metal strip on the bottom. And then the battery, which is off camera, is hooked up to the two metal strips. So first I'd like to measure the voltage across this circuit. And if you look on the multimeter there, it's pretty close to 1.5 volts, a little bit less than 1.5 volts. So that bears out our prediction about the voltage here being 1.5 volts in each case. Now I'm going to measure the current through the last resistor first. So I got to reconfigure my multimeter to measure current. And I'm going to put the bottom probe here on the bottom strip, and then I'm going to just kind of hold my other probe on my resistor here. And that's about 27.3 milliamps going through this last resistor. And our prediction here was going to be 30 milliamps, so it's pretty close. Now I'm going to kind of bend the wire up on this middle resistor, and then put my little metal bar down here and measure the current going through the middle resistor. And when I do that, I get about 33.3 milliamps. And our prediction here, to remind you of that, was going to be about 37.5 milliamps, so it's pretty close. And then finally, the current going through the resistor on the left. Again, put my meter here so you can see what that is. And that's about 43.1 milliamps. And our prediction was 50 milliamps, so a little bit less than that, but at least it's in the ballpark. Okay? Now I have a little confession to make here. Off camera here, I don't have just one single battery, but I have a whole battery pack of batteries in parallel. And the question is, why would I do that when we already talked about batteries in parallel don't give you a voltage advantage? So the voltage of this battery pack should be 1.5 volts, which is the same as the voltage of a single battery. Well, there's one thing I didn't talk about that was talked about in the other films, and that is each of these batteries has an internal resistance. And because I'm trying to draw so much total current out of the battery pack, the internal resistance has a tendency of reducing the voltage across the battery itself, which is called the terminal voltage. So the more voltage you try, or the more current you try and draw out of a battery, the more the voltage, the terminal voltage across the battery is going to start dropping from its nominal value. So if I were to just use one battery here instead of this whole battery pack, the voltage I would measure across my circuit would no longer be 1.5 volts, but it might drop down to 1.2 or lower volts, because I'm trying to take so much current out of the battery. and therefore the resistance of the battery becomes a factor. We'll talk more about the internal resistance of batteries later. Okay, the last current we need to measure is the current that's coming out of the whole circuit going back into the battery. So I'm going to make a little break here, and I'm going to hook up going back into my battery pack is that clippy, and then I'm going to take the other guy and I'm just going to put him on the end here, and I guess I'll move this closer so you can see what we're measuring here. So the total current coming out of this thing is going to be 84.6 milliamps, and we said that that the total current should be equal to 118 milliamps, so that's quite a bit less. And again, I think that's because we're kind of maxing out our battery here. Now, let me see if I can do this current measurement again. Maybe I need to press down harder or something. It looks like the only maximum I'm going to get out of here is going to be 84.6 milliamps. That's telling me that we're kind of maxing out our battery pack here. But if this were an ideal battery that didn't have any internal resistance and could supply all the current that I needed, then I would probably get something a lot closer to the predicted 118 milliamps. Now I'd like to say one more thing about this particular circuit. We figured out the total current going into the battery, which incidentally is the same as the current going through the battery and the current coming out of the battery, by summing the individual branches, the individual branch currents together. So you can think of the total current coming out of the battery splitting up into three branches, kind of like three branches of a river, and then all this current coming back together again and going back in and through the battery. And we could figure out that total current by figuring out the current in each branch and adding it together. Well, there's another way I can figure out that total current. I could figure out the equivalent resistance of these three resistors in parallel, and then just replace these three resistors with a single resistor of that value, and then figure out, well, what the current would be in that simple circuit. And that should be the same as the 118 milliamps that I have here. So let's do that really quick. Remembering the formula for parallel equivalent resistance, 1 over R equivalent would be equal to 1 over R30 in this case, plus 1 over R40, plus 1 over R50, and that's going to be equal to 1 over 30 ohms plus 1 over 40 ohms plus 1 over 50 ohms. And remember how we do that in our calculator here. We take the 30 and then we hit reciprocal, and then we add that to 40 reciprocal, and we add that to 50 reciprocal, and then we hit enter to find out what the sum is, and then we go second function answer to bring back that number and hit reciprocal again because we want the reciprocal of the whole thing here. And when we do that, we get 12.8 ohms basically. So I can take this entire circuit up here and basically replace it with a circuit that looks like this, where we have 1.5 volts and 12.8 ohms. And the current that we would measure going through that circuit should be equal to the same value as we got here, the 118 milliamps, okay? So let's do that using Ohm's law. That's V over R, in this case R equivalent. And the voltage is 1.5 volts. R equivalent is 12.8 ohms. And 1.5 divided by 12.8 is equal to 0.117 amps, which is 117 milliamps. So given the rounding error, that agrees well with the 118 milliamps that we got using the other method. Now I want to point out one thing about the finding the equivalent resistance of a resistors in parallel. Notice that this 12.8 ohms is less than any individual resistor. And that's always going to be true. Your equivalent resistance for resistors in parallel will always be less than the smallest resistor in that group. In a similar vein, if you have resistors in series, the equivalent resistance is going to be larger than the largest resistor because you're simply just adding all the resistor values together. And if you kind of want an idea of why that makes sense, imagine you have those little tiny straws like you get for stirring coffee. That's one of those straws. And let's say you were going to kind of tape them all together to make one big long straw. And then you tried to blow through that straw. Can you see that it would be more difficult to blow through a bunch of these skinny straws hooked together to make one long straw than it would be to blow through just a single straw by itself? That's because there's more resistance to the airflow in this long skinny straw than there is in any individual straw. And that's kind of like resistors in series. There's more equivalent resistance than any single individual resistor in that group. But if you took the straws and you did it this way instead, you took all the straws and you put them next to one another, and you blew through those straws, kind of like pipes of Pan, it'd be a lot easier to blow through three straws this way because the straws are in parallel and they resist the airflow less than any individual straw. And this is kind of like resistors in parallel have less resistance equivalent than any single resistor in that group. Okay, I'd like to analyze a more complicated circuit. This one has a 6-volt battery. The current leaves the battery and goes to this 10 ohm resistor. Goes to the 10 ohm resistor to this point here, and then it splits up. Part of the current comes down here through the 30 ohm resistor and then back into the battery, and part of it goes through the 20 and then the 40 ohm resistor and then back into the battery. All these little red circles represent various kinds of meters. These are voltmeters measuring the voltage across the 10 and the 20 ohm resistor, and then another one over here measuring the voltage across the 30 ohm resistor, and one over here measuring the voltage across the 40 ohm resistor. Then we have some current meters. A current meter here measuring the current through this branch, a current meter here measuring the current through this branch, and then a current meter here measuring the current going back into the battery. I'd like to remind you that current meters behave like wires. The circuit doesn't even know they're there because they have zero resistance, whereas voltmeters behave like they have infinite resistance. So the circuit doesn't even think there's anything connected when a voltmeter is in place like that, measuring the voltage across something. So I've cleaned up the diagram down here without the meters. That might make things a little bit easier to see what's going on. Now the first step in analyzing this circuit is to try and figure out what the equivalent resistance is of all these resistors. So we want to combine them in such a way that we can replace all of these resistors with one resistor, and that will enable us to figure out the total current that's going through the battery. So we start over here and we realize that the 20 ohm and the 40 ohm resistors are in series with one another. All the current that goes to the 20 ohm resistor must also go through the 40 ohm resistor. They're kind of stacked together in series. So that means the equivalent resistance of these two resistors is just the sum of the two resistance values, which is going to be 60 ohms. So we can take this circuit and reduce it to this circuit here with the 10 and the 30 still there, but now these two resistors replaced with a single 60 ohm resistor as shown in this circuit. Okay? Now what I'd like to do is figure out, well, what is the equivalent resistance of these two resistors? Well, they're in parallel. The current going into this point has to split up. So that means that these two resistors are in parallel. And we have a rule for that. We see that the reciprocal of the equivalent resistance would be the sum of the reciprocals of the individual resistors. It looks something like that. And if you work out that math, that means the equivalent resistance must be equal to 20 ohms. And that makes sense because that 20 ohms is less than the smallest resistor of these pair, which is 30 ohms. So now we're left with our final circuit here. We have a 10 ohm resistor in series with a 20 ohm resistor. So the equivalent resistance is just the sum of 30 ohms. So now what we have is we have a simple circuit that looks like this. One 30 ohm resistor and a voltage of 6 volts. I guess I should have put the 6 volts and all these others as well. So the current going through this circuit is just equal to V over R, which is 6 volts divided by 30 ohms, which is equal to 0.2 amps. That means that, coming back to this diagram, that the current flowing out of the battery is going to be 0.2 amps, as well as the current flowing into the battery is 0.20 amps. Okay, now that we know that the current coming out of the battery is 0.2 amps, we can figure out what the voltage is across that 10 ohm resistor, because all of that current is just going to go right into that 10 ohm resistor, and we know that V is equal to I times R. This would be the current going through the resistor, and this would be the value of the resistor itself. So in this case, this would be equal to that 0.20 amps times the value of the resistor, which is 10 ohms, and that's just going to simply give us 2 volts. That's what this voltmeter would measure. It would measure 2 volts. So I'm just going to write 2 volts above this resistor, because that is the voltage drop across that resistor is 2 volts. Now, if 2 volts is dropping across that resistor, that means that the voltage at this point across this whole circuit here, if I put my voltage probes between these 2 points right here, that must be 4 volts, because remember, the sum of the drops has to equal the boost of 6 volts. So the voltage across this 30 ohm resistor, which is the same as the voltage drop across this whole network here of resistors, and that voltage drop here must be 4 volts. Okay? So that's going to give us the voltage drop across the 30 ohm resistor. It's also the voltage drop across these two as well, because these 2 resistors together are in parallel with that. So the voltage drop is the same everywhere. So I'm going to put a little 4 volts. Oops, got to do it in green here to follow my convention. I'm going to put a voltage drop of 4 volts across this resistor, okay, which is also across these 2 resistors. Okay? Well, now I know the voltage drop across the 30 ohm resistor. I can now figure out the current going through it, because again, according to Ohm's law, I is equal to V divided by R, which in this case is going to be the 4 volt drop divided by 30 ohms. So 4 volts divided by 30 ohms. And that's going to give us a current of going through the 30 ohm resistor of 0.133 amps. Okay, that's 4 divided by 30. Just let me make sure that's correct. Okay, so now I can put that in the diagram here, that the current going through here is 0.133 amps. Well, if I had 0.2 amps of current going through here, and then 0.133 amps splits up and goes down here, that means that the current going through this part of the circuit must be the original 0.2 amps minus the 1.33 amps that kind of tails off that way. Okay? That means if I subtract one from the other, my 0.2 amps minus my 0.133 amps, what that's going to give me is going to be 0.0667 amps. That is going to be the current that splits off and goes this way. So I'll write that in there. 0.0667 amps. Now, that current is the same current through both these resistors because they're both in series. And anytime you have resistors in series, the current is the same. So it's the same current going around the bend here, the same current going around the bend here. Same all the way up to this point where it joins this current here and becomes 0.2 amps again. Okay, 0.20 amps. So you kind of get a picture of what the currents are doing as they go around the circuit. Okay, now that we know the current going through this sort of part of the circuit, we can figure out what the voltage drops are going to be across each one of these resistors. Because we know that from Ohm's law, V is equal to I times R. So coming back over here again, V is equal to I times R. So let's look at the 20 ohm voltage drop first. That would be the current going through it, which we've already determined to be 0.0667 amps. And we multiply that by the resistance of the resistor, which is 20 ohms. And when we do that, we get 1.33 volts. Let me just confirm that here. 0.0667 times 20. Yeah. Okay, good. So now I can put that in my diagram as the voltage drop across the 20 ohm. So I'm going to put 1.33 volts. In a similar vein, I can figure out the voltage drop across the 40 ohm resistor. So in this case, V is going to be equal to that same current, because it's going through both resistors in series, of 0.0667 amps. And we multiply that now by 40 ohms. And what we get when we do that is basically double this, which is 2.67 volts. Okay. Sorry about that. I went off screen there. That's the voltage across the 40 ohm resistor. And so I'm going to write that in there. 2.67 volts. And now I believe we have everything that we wanted to know for all these voltages and currents. I just want to point out one more thing here. This kind of leads into the next series of videos. If I go around a loop, the voltage drops equal the voltage boost. So I have 6 volts of voltage boost going around this outer loop, and that we have 2 volts of drop here, and 1.33 volts of drop here, and 2.67 volts of drop here. And if we add up all these drops, 2 volts plus 1.33 plus 2.67, what we get is the 6 volts of boost. But I could also go around a loop like this and the same thing happens. I get 6 volts of boost. If I go around this inner loop, 2 volts of drop, 4 volts of drop, the boost equals the drop. In fact, I could even go around this loop here, and it's kind of a little bit tricky because I'm kind of going the opposite direction of the 4 volts here, and so I have 4 volts backwards, and then 1.33 volts of drop and 2.67 volts of drop. And these two together will add up to 4 volts because as I go around the loop I'm going backwards. So it's not really a voltage drop, it's kind of a voltage boost because I'm going backwards. So the boost in this loop would effectively be 4 volts because I'm going backwards through the resistor, and that equals the drop going forwards through these 2 resistors. That's called Kirchhoff's loop law. And we're going to look at that in more detail in the next set of videos. The other thing I want to point out is that the current going into a little junction, which in this case for this junction is 0.2 amps, is equal to the sum of the currents going out of the junction, which is 0.133 amps plus 0.0667 amps. Similarly, for this junction down here, the current going into it is equal to 0.133 amps going this way and 0.0667 amps going that way. That's equal to the current going out of it, which is 0.20 amps. That is called Kirchhoff's node rule, and we're going to learn more about that in the next set of videos.